Welcome to Lab 4 Magnetic Dipoles and the Bar Magnet. The purpose of this lab was to examine and calculate the magnetic field of a bar magnet and to understand how it acts like a dipole and creates a dipole field. The results of this lab were that we calculated a magnetic dipole moment of 5.97 amperes times meter squared and an N value of negative 1.6789. And as you can see, also the computed off-axis magnetic field, which is a mouthful to say, so I'm gonna just let you read that. The magnetic field of the bar magnet in the form of distance dependence is calculated with that first equation, which is equal to k times r to the n, where k is some combination of constants and r represents some distance, and n is the value we raise r to, which should be negative because we know that distance is always inversely proportional to the magnetic field. The farther away we get from our source, which is in this case the bar magnet, the weaker the magnetic field is. Below this, you can see the magnetic field for a dipole, which is equal to Km times 1 over r cubed times 3 times the dot product of mu times r hat, and then times r hat again minus the mu vector. We also went over concepts of general dipole fields in this lab and the Biot-Savart law of magnetism. In this lab, the system was the magnet, the bar magnet we used in the experiment, and the surroundings was the earth. This experiment involved locating the magnetometer inside our phones relative to the magnet we were working with and also trying to neglect the Earth's magnetic field. Here are some of the values that we calculated in the lab. R20, R70, all the way to R220, those are different magnetic field values of the bar magnet we calculated at different distances, and specifically for the X component. And if you look to the right on the graph, you can see we have the plot of the magnetic field, the X component, taking a natural log of that versus the X component, which is the natural log of the distance of that calculation. And we see we have a linear slope here, like a linear plot, and the equation y is equal to negative 1.6789x minus 12.168, where negative 1.6789 is our n value and negative 12.168 is our natural log of k value. You can see values for the off-axis field below, where we calculated a deep perpendicular measurement of 0.154 meters, and also we calculated the total net field by the bar magnet to be 1 times 10 to the negative 4 microteslas. Here I calculated K to be 5.194 times 10 to the negative 6 by raising the base of the natural log E to negative 12.168. For the coding, you can see the dipole of a magnetic field equation, which is equal to, once again, Km times 1 over the magnitude of the distance squared, not squared, cubed, and then times the rest. And then to the right, you can see the different observation locations we used in this lab. The first two are the parallel observation locations we had, um, and where we measured the magnetic field for those at, and then the rest are perpendicular locations for the y and the z axes. And then the rest is also things to deal with location and positioning. And this is the code that we use to calculate the magnetic field at the 45-degree angle. And this was the main one that was off axis and required a little bit more computation. Here is a picture or a graph or demonstration of how the magnetic field looks. And as you can see, we have our two orange arrows, which represent the parallel magnetic field of the bar magnet, and the cyan or blue arrows represent the perpendicular parts of the magnetic field of the bar magnet, and the magenta represents the 45-degree measurement of the magnetic field of the bar magnet. What if we didn't compensate for magnetic north of the Earth? If we did not compensate for magnetic north, then our measurements for the magnetic field would not have been purely due to our magnet, and our curve or slope of our natural log of the magnetic field in the x component versus the natural log of the distance relative to the magnetic field would no longer be linear. And what if we place two bar magnets end to end? If we place two bar magnets end to end, then and pointing in the same direction, their magnetic moment would double. And if we put them together oppositely, the magnetic moment would nearly cancel. Thank you for watching this video.